Hello, my name is Kim, and I'd like to present about characterization of temperature-dependent debonding damage in highly particle-filled thermoplastic composites. There are 4 parts of my presentation. First, I'm going to talk about motivation and research objectives on our research, and second, materials and modeling will be dealt with, and third one is about
Can you speak a little bit louder?
Okay,
Please,
thank you. Third one is about results and discussions. And final, some will be followed. And first of all, I want to talk about highly particle-filled polymer composites. Highly particle-filled polymer composites, and from now on, I'm gonna shorten it, HPFPC, are used in many industries and is typically used in biomedical and solid propellant. And these composites, as you know well, are composed of particle matrix and particle to matrix interface. In these composites, polymers which act as a matrix have intrinsic qualities like corrosion resistance, lightweight, and ease of processing, but combining them with fillers can enhance their limitations, such as low strength and stiffness. Adding various fillers can significantly alter properties, like these comments. But in this point, it is necessary to focus on the fracture behavior of it caused by particle filled highly. The fracture behavior of HPFPC is significantly influenced by how cracks interact with individual constituent faces at the micro scale. There are 3 basic fracture mechanisms. First one is particle fracture, and second one is crack deflection, and third one is interface debonding. And in particular, the understanding the behavior of interface debonding is important because it significantly affects the energy absorption, fracture resistance, and load transfer efficiency. Temperature dependence of HPFPC is also important thing because the fracture behavior of it can vary with temperature. And as you can see these figures, it can be confirmed that the particle matrix interface characteristics appear differently depending on the temperature. There are some literatures regarding to the things I mentioned. One of these literatures has investigated the mechanical behavior and fracture mechanism of HPFPC at different temperatures, like this figure. But in this paper, it was difficult to find the property relationship caused by debonding because it did not identify the mechanism of debonding as the interface strength varies with temperatures. So at this point, this turning point of our research. Here is the research objective of our study. First one is developing model using coefficient modeling to predict debonding damage behavior with respect to temperature. And second one is identifying debonding damage behavior involved setting specific particle shapes, size, and distributions. And next is materials and modeling. in our study, we conducted uniaxial tension tests for 6 temperatures. And in case of the mechanical properties of matrix and particles, refer to literature results. For particles, linear elastic properties were used. And for polymer matrix, the coefficients of your hyperelastic model were used. And this is the equation of the your hyperelastic model. And regarding to viscoelastic properties, the coefficients based on derived from Prony series and based on generalized Maxwell model. And this is by FE modeling to simulate the temperature dependence interface debonding. The microstructure of HPFPC is characterized by 2D RV model, and it is composed of randomly distributed particles and matrix and particle matrix interface. And we applied periodic boundary condition, which can simulate the behavior of entire material by modeling only one unicell. And this table is about details of our FE modeling. And this slide is about cohesive zone modeling for defining interface characteristics. There are 2 ways of cohesive to model interface by using CGM. And one is cohesive contact, and the other is cohesive elements. And in our study, interface properties were defined by using cohesive contact. And based on the literature, the cohesive stiffness and damage of interface were defined by using this bilinear cohesive law. And we performed case studies regarding to the effects of particle shape, particle volume, fraction, and size on debonding. And from now on, I'm going to talk about results and discussions. After we conducted the uniaxial tension test, we observed the fracture surfaces for temperature. And as you can, through these same images, we found that as fracture surface moves from low to high temperature region, the fracture mechanism changes from particle fracture and crack deflection to interface debonding. And this results is relation between temperature and normalized stiffness, and this result used to define interface properties for temperature. And this is results of our simulation. As you can see, these figures and these graphs, as the temperature increases, like this voice caused by interface debonding increase. And the results of internal energy change at its temperature and show that the higher temperature, the lower internal energy, which can be seen as a result of loss of surface energy caused by debonding. And next is the effect of particle shape on interface debonding. In here, the ellipse is set to reflect the effect of aspect ratio, and by choosing a pentagonal shape with corners and angles, we wanted to see the difference of stress concentration and interface debonding effect. And as you can see, these results, stress was concentrated around particles, and with large aspect ratios or large particles that were strongly influenced by low direction. And for all particle shapes, the internal energy change at its temperature showed that the higher temperature and the lower internal energy which was a result of surface energy being lost due to debonding. And last case is the effect of particle size and volume fraction on interface debonding. It found that the smaller size particle size and the higher particle fraction, the more evenly distributed the stresses and less debonding. In cases 2 and 3, where particles were evenly distributed, the internal energy generated over time was similar. And in all cases, the internal energy tended to decrease as the temperature increased. Before concluding, I'd like to share our research plans. And in our study, I presented only focus on micro scale, but it is necessary to connect to macro scale. So we're gonna construct a prediction model of mechanical properties using our findings and these literature reference equations. Finally, we have 3 main conclusions. First one is the internal energy change results at each temperature indicated that as temperature increased, the internal energy decreased. Second one is the investigation into the effect of particle size and distribution showed that stress concentration occurred in areas where large particles were present in the matrix. It was also found that the smaller and the more uniformly distributed particles result in relatively less debonding. And last but not least, when comparing the influence of particle shape, size, and distribution across 3 different temperatures, it was found that the trend with respect to temperature remained consistent, but particle distribution and size significantly impacted the extent and uniformity of debonding. This is all of my presentation. Thank you for your attention.